Awesome.
Okay. I'm very delighted to have Laura actually show up and be here for this talk. Laura is the assistant professor at University of Maryland in College Park, and she uses LiDAR data to understand and monitor forest carbon dynamics at global scale. I guess she's best known to us as the lead behind GEDI, which all of us have been, many of us been using and know and love well. So it's really quite a great opportunity to hear from Laura directly about GEDI and ICESat. So thank you so much for joining us, and it's all yours.
Awesome. Thank you so much. It's an absolute pleasure to join you. Wish I could be there in person. I can't travel as much as I used to because I have a baby now, but it's really great to be able to connect digitally in these kinds of forums. So thanks so much for the invitation. I'll just quickly start by saying that this is representing work from like many people, both on the GEDI and ICESat-2 science teams, as part of a big biomass harmonization effort that we've got between agencies and institutions. And then many co-authors who have helped us build the GEDI biomass algorithms, including David Coombs. So one of probably our earliest collaborators on that effort, way back in the day when I did have the opportunity to visit you in person at Cambridge. Okay, so this can be like a little informal, so feel free to jump in with any questions or clarifications. I'm going to pretty much just talk about mission products and how we're using them and where we're going in the field of satellite LiDAR for biomass mapping. So a lot of this is going to be like kind of, you know about it, but just for those of you who are maybe more on the computer science side and don't sort of follow global carbon cycle stuff, the science context of most of what I'm going to be presenting today is indeed with respect to the global carbon cycle and carbon budgets. So we all know we're in a climate crisis. A big part of that is related to vegetation. So for sure, fossil fuel emissions are driving the crisis. But one of the reasons that I really love studying forests is that there's a lot of hope there. So we can manage forests toward climate mitigation. They're certainly not going to like save the world entirely. We can't just pollute, as much as we want and assume that the trees are going to grow and absorb all of that pollution. But certainly there's a lot of opportunity to manage forests for this aim. So we know that vegetation stores a lot of carbon. We know a lot of that carbon gets lost from deforestation and degradation. We know a lot of it gets sucked down through regrowth, through just like baseline photosynthesis in intact forests, etc. But we have huge uncertainties on these numbers still. And a large part of that is because we haven't had really good spatially explicit maps of forest carbon sort of before this latest generation of LiDARs. And I'll talk about that a lot today. At the same time, we have so much attention and so much funding in this field because of its climate relevance. So back in 2020, there has been a commitment at COP26 to end deforestation by 2030 and then start reversing it. So this is like a really big declaration. 141 countries signed on to it, covers 90% of the global forests in those countries. And there are the sort of big excitement here, because this is not the first pledge, but the big excitement was these financial commitments. For example, 1.7 billion to support indigenous peoples, 1.5 billion to conserve the Congo Basin in particular, which has arguably been a little bit under resourced compared to the Amazon, for example. So this is really exciting. And our research really fills some knowledge gaps here. At least in theory it does, but there are some bridges we need to build before our remote sensing forest carbon research can fill these sort of policy needs. Okay, but we have these global commitments, and we can use satellite data to essentially make sure that they're actually being met. Here's an animation from Matt Hansen's group, also in our department, showing Landsat data looking at forest cover in an area of the Brazilian Amazon that happens to be an indigenous managed protected area. So this is from 1985. Like, we have had 50 years of monitoring these forests from space. We have really wonderful satellite imagery, again, not carbon, but satellite imagery showing this. So here we have a bright green forest. And then as you see time tick on, we see the Landsat monitoring showing that we're having a lot of forest loss around this protected area. So the protected area is that black line here. So you can just see that that forest is disappearing. Lots of deforestation going on in Brazil. And as we approach, this actually doesn't even go through to present, but you start to see encroachment inside that protected area as well. So these are like pretty alarming animations. And Matt Hansen's group is kind of, I would say, the world leading research group that is doing this kind of work. Now, this is not carbon loss. This is forest loss, right? Because we didn't know how much carbon was stored in those forests to begin with. And that's really where the LiDAR piece comes into this. So welcome, GEDI. So for those of you who don't know, GEDI is the Global Ecosystem Dynamics Investigation, GEDI, like pronounced like Star Wars, because then we get to do all the fun Star Wars stuff. And like, who wasn't going to fund a space laser called GEDI, right? So, and we lean really heavily into that whole like Star Wars stuff. All right, so here's the much of the mission team way back in 2018, before COVID, when travel was simple and exciting and nobody had to wear a mask for group photos, and it was a gentler place. So this is us down in Florida. This is a SpaceX Dragon capsule launch to the International Space Station. So GEDI wasn't the only thing going up. And this was like kind of like the early days of the Elon Musk recyclable rockets. So like the rocket went up and then came back down and then it fell over and then that's all anyone cared about. But it was really exciting. So forgive me, but I'm going to play kind of like my home video of the launch.
Don't start shouting. 10, 8, 7, 6, 5, 4, 3, 2, 1. Yes. Yes. Oh yeah.
It was extremely exciting.
Cool. It's done.
It also kind of went like a bit slower than we expected. Doesn't go on too much longer, I promise. It's sort of, and we all just started dancing around, so I stopped recording. But yeah, so that was the GEDI launch, and it obviously was successful. Got up to the space station. And so once it's on the space station, this is the mission animation for what it looks like. So for those of you who don't really know what GEDI is, it's about a refrigerator-sized box that like got launched up to the space station there. It's plugged into the side of this exposed module that Japan manages, and it's got 3 lasers in it. One of those lasers is split into 2 beams. So it's 4 laser beams coming down and hitting the ground. And then those are bounced back and forth to make these 8 ground tracks. So GEDI data, like if you just download the raw data, you're going to see all of these spots in these 8 lines. The spots are the individual LiDAR footprints. So one laser illuminates about a 25-meter circle and like washes the forest with photons. And those photons reflect back off whatever they hit to the space station, or to the GEDI instrument, and record LiDAR waveforms. So these waveforms, which is like here in orange, but in reality, they're near infrared lights. We can't see them. They represent the 3-dimensional structure of whatever they hit. So like the first photons bounce back off the very top of the canopy, the last photons bounce back off the ground, and kind of like the area under the curve above the ground is like the structural material, the woody material. If you're in a forest, if you're hitting a building, it'll be, building material. But really GEDI it's the first LiDAR ever designed for forest structure monitoring and mapping. And so we translate these LiDAR waveforms into a whole suite of different data products that are then used by scientists, hopefully by policymakers, to inform stuff. So this is the spatial distribution of GEDI under a single pass. So as the ISS goes over, you get these 8 lines, and each individual spot, as I said, is about a 25-meter diameter circle. Varies a little bit based on like slope and some ISS specs, but it's about 25 meters. And then those are spaced 60 meters between shots on a single line. And then those lines or tracks are spaced 600 meters apart. And the whole swath is about 4 kilometers. So that's what the data looks like. As I said, of these 3 lasers, one of them is split into two beams, which are about like a little bit less than half the power of the original like strong laser. And those are called coverage beams. So like half of the data are from these like really strong lasers and half are from like a laser that's been split. Almost all of that data is still really, really good. But if you're in like a super dense forest, or you're collecting data during the day when you have a bunch of like solar background stuff, the coverage laser is not going to be quite as good as the full power laser. So you might want to filter your data. Okay, but we're getting into the weeds there. So this is what the data looks like spatially. And then if you grid it, and all of the gridded data products for GEDI are 1 kilometer. So you take all of the shots in each 1 kilometer cell and you grid them. So here's global topography, or not quite global, but we'll get to that. Topography. Canopy height, so that's like the top of the waveforms minus the bottom. And then biomass, and this is where I focus my research and really where the rest of the talk's gonna focus. So woody above ground biomass, not the first biomass product out there, not the last biomass product out there, but unique in that it is built entirely on satellite LiDAR. So it's not being like extrapolated with some sort of optical stuff that we know saturates. And way, way more, like orders of magnitude more satellite LiDAR than we've ever had. So there's like old biomass maps that are trained with like a tiny amount of ICESat glass data, and then extrapolated with optical data. We know that those are going to saturate in like really dense tropical forests, for example, whereas GEDI in theory doesn't. So there's like, this is like a totally different type and revolutionary type of biomass map, which sometimes gets a little bit lost when we're kind of communicating this stuff more broadly, because people are like, another biomass map, and we're like, no, like kind of the first one. All right. So how do we make those biomass products? This is like embarrassingly simple if we're talking to like a computer science crowd, because these are like basic OLS models. Like it's like the most basic thing in the world. So what we do, the remote sensing is a little bit fancy, but like the statistics are extremely simple. So what we do is we knew that originally GEDI was only supposed to be like a 2-year mission. And we were like, there's no way we can go all over the world and collect enough data to calibrate these models in 2 years. And we don't have the budget for it. So what we can do is we can take airborne LiDAR that already exists and make it look like GEDI. And so we reached out to like everyone we knew, like the David Coombses of the world. And we said, hey, anyone have field data that's coincident in space and time with airborne LiDAR? And can you like share it with us so that we can build these global models? And a lot of people said yes. And so what we do is we take the airborne LiDAR, make it look like GEDI through a simulator, and then compute the same sort of waveform metrics that we get in on-orbit GEDI, and build these statistical models that are just predicting biomass as a function of what we call relative height model or metrics, which are these sort of predictor, or they're these like statistical descriptors of the waveform distribution of heights. So it's essentially the height below which some percentage of the waveform energy has been returned relative to where we think the ground is. So you have to like pick where the ground is in these waveforms, and then you compute these RH metrics. So like RH98 is like maximum height. Okay, so here's where the data are that are in our models. And you note that there is a bunch of stuff that is north of the GEDI domain. I use that for ICESat-2, so we'll talk about that in a second. But this is the spatial distribution. So like we got a lot of data, but certainly not everywhere. This is not truly globally representative. Look at Central Asia, we've got like pretty much nothing. And that's, I mean, we're kind of growing as we go. We then take the world, we divide it up into these plant functional types, which are like super broad strata where we fit models and apply them. So we're doing like evergreen broadleaf trees, needle-leaf trees, deciduous broadleaf trees, and then this like big catch-all that we call like woodland, grassland, shrubland, but it's just like kind of low dry stuff. We put it all in a model. So there's like a lot that we could do to improve this. And if people want like more kind of refined models for GEDI, we're working on, you know, a bunch of side projects to improve those for various like science and applications cases. Okay. So this is just like an example of how simple this is. So this is a waveform from Brazil, from the Brazilian Amazon. And we predict biomass as just the square root transform of an OLS model that's predicting based on RH50, which is kind of like mean height, and RH98, which is like max height. So if you plug in all of the waveform metrics here, which in this case, RH98 was 29 meters. So like that's kind of maximum canopy height. RH50 was 19. Plug it in, we have to do like a bias correction back transformation thing. because we did the square root transform. Won't get into the details of that, but essentially for this waveform, you have a predicted biomass of 209 tons per hectare. And that's kind of like the classic measure of biomass. Okay, so it's that simple. Now we're not like closed-minded to doing fancier things. We did a bunch of like, tests of different statistical forms, being like, okay, let's try like some basic machine learning stuff, some like boosted gradient regression stuff, boosted trees, random forests, whatever, just PLS in the sort of more parametric world. And nothing was actually transferring better than just like a classic OLS to areas that didn't have training data. So like, we think that the whole machine learning, deep learning world is fantastic if you have training data that is like totally representative of whatever you're trying to map. But if you're trying to extrapolate from one area to another, we were actually finding that those fancier models weren't working as well. So that's like an aside we can talk about if you want. Anyway, so we have like a bazillion amazing partners and collaborators who have helped us with the database, and it continues to grow, and we are always looking for more data. And I'll talk about that again in a little bit. But once we have those models, we apply them to on-orbit data. So there we have the simulations, the models that we develop, we apply them to these footprints on orbit, which are not wall-to-wall mapped, right? And then we calculate 1 kilometer mean biomass with the associated uncertainty. So you take the mean of all of the shots in each 1 kilometer cell, and then there's like kind of some fancy statistical algorithms to do the uncertainty using hybrid inference here, which I won't really go into in detail unless people ask. And then we calculate like wider area estimates. So in the official GEDI biomass paper, there are national totals for all of the countries that fall fully within the GEDI domain. And those have now actually recently been updated. Okay, so there is, I should say the last little thing, there's a brand new 1 kilometer gridded product that just launched, like I think a week and a half ago, that's available to download. So if people have been playing with the GEDI biomass map and you're like, there's so many gaps, it's like, it's fair. Or maybe you are like, there's no data in Cambridge. It was funny because I was making this animation to show the difference between like the old coverage that's on the left, that's the existing, the past product, and the new one that just has like a lot more on orbit GEDI coverage. And I just thought it was funny that like Cambridge is like right at that cusp. So I don't know how far up like the data actually go, but it's like a little funny. It's like a land of riches and then nothing. But anyway, if you look at like some of the areas more in the tropics, you can see just so many data gaps are being filled in by GEDI over time. So I encourage you to check out that new version of the L4B product. The other cool thing there is it's not just filling data gaps, but there have been some refined data filters. So there are some areas where like there's like some crazy high biomass estimates from L4A that were like, we think triggering on like low cloud, or like there's some funky elevation stuff going on. So that's been refined as well. So there are some pixels that like actually disappear, but that's because they were errors. Okay. And then let us know how that looks. Okay, so I'm going to pivot now. As you know, from where you are in the world, GEDI is fantastic for tropical and temperate forests, but then as soon as you get to a certain latitude, it literally disappears, right? So I'm Canadian, and that was a bummer for a lot of Canada. And so we're like, okay, if we want a truly global data set, we're going to need to do something for those more northern forests. And that's where NASA's ICESat-2 comes in. So this has been kind of like a side project that I've been leading for several years that I'm pretty passionate about, is filling GEDI's northern data gap. So ICESat-2, shockingly, not designed for forests, designed for ice. So this is another satellite LiDAR mission. We're very like LiDAR rich at the moment. And it was actually a bit of work to convince NASA and others that we needed to keep GEDI up, because they're like, but you've got ICESat-2, it does the whole globe. And we're like, ugh. It's totally photon starved in a lot of the tropics. So ICESat-2, fantastic for mapping ice sheets and ice sheet change with like extreme precision. But the lasers are way weaker than GEDI, so they don't penetrate through really dense canopies the same way. But for relatively short, relatively open forests, like you find at high northern latitudes, this data is actually really, really great. And so we took the same approach to GEDI to make these biomass models, but we did it simulating ICESat-2 instead of simulating GEDI, and applied them to ICESat-2 data for the boreal. And we mapped down to 50 degrees north. So like, I think that that's online too. It's the full boreal and then down to 50 degrees latitude. So if you are like, I have no GEDI data, I'm just north of 51.6 or whatever it is, this data exists. So here's another option for you. I can't promise how good it is in the UK. We haven't validated it there, but hopefully it's okay. We've just clipped it to the boreal domain in this image. So this was an open data or an open science exercise. NASA's doing a big transition from open data to open science. Oops, let me see if I can play this animation. And it's so beautiful. So this was all done like, it's actually wall to wall. We extrapolated the ICESat-2 with Landsat. And this is representative of around 2020 conditions. So we did this big launch of this, God, it was like a couple of years ago. We used this like fancy new NASA kind of approach to making big maps. And they wanted us to make this animation for the hyperwall at AGU, one of our big conferences. And we're like, yeah, it's going to be beautiful. And I don't know if you guys noticed this, but there is this like missing tile in, I don't know if you see it there. But to me, I'm like watching, and I hadn't noticed it before. And then it's up on this massive hyperwall screen. And I'm like so excited to see our beautiful baby product like up on the big screen. And then all I can see is this like awful data gap of one missing tile. Anyway, it kills me. So we're working on redoing this for this AGU with an updated version of this product that doesn't have gaps. But there you get the general gist of what it looks like. Okay. So I talked about this is like computer sciencey. This was made on what NASA calls an open science platform called the Multi-Mission Algorithm and Analysis Platform, MAAP or MAP. Kind of annoying they called it MAP, because if you're doing biomass mapping on the map, it's very confusing to communicate, but it is what it is. It's called what it's called. And this was bilaterally developed between ESA and NASA in recognition that both agencies had satellites that were coming up that were doing similar things scientifically, and that data fusion between them makes a lot of sense. So on the NASA side, this is GEDI first, but then NASA ISRO's NICER, which is a forthcoming L-band SAR mission. And then on the ESA side, ESA's biomass, which is a P-band SAR mission. And both NICER and ESA biomass are launching in 2025. So like it gets worse. So we're doing biomass mapping on the map with biomass data, and there's like also a biomass library. It's just, anyway, it becomes a whole mess to communicate outside of writing, but that's fine. So this platform, I'm like obsessed with it. It's designed for collaborative open science, especially during COVID. This is like, you launch it in a web browser, it's all linked to AWS, and you have full access to all the NASA and ESA like data stores. And it's super collaborative. So I'm like doing stuff in my Jupyter notebooks and then sharing it seamlessly with the rest of my team, no matter where in the world. They were like huddled during COVID, and like, you know, they're seeing my code in real time, I'm seeing their code in real time. It was like being in a big virtual computer lab. And so I'm a big fan of it. This is not the only approach, but NASA is fully going into the open science realm, which means it's like all of the code for all of the future NASA products will be available, not just the products themselves, which is like a huge shift in vulnerability. I am not a trained computer scientist at all. I'm a self-taught coder. My code is a mess. All of my collaborators get annoyed about it all the time. I'm doing a lot better now, but but all of that code, all of that mess is fully visible to any of you if you want to see how messy it is. The repos for this is called ICESat-2 Boreal, and it is available to look at in real time. Okay. So for that ICESat-2 Boreal product, as I said, we take ICESat-2, we apply biomass models that are fit the same way as the GEDI models, and then that becomes our training data for these wall-to-wall maps. ICESat-2 doesn't have the same kind of spatial density as GEDI, and so if we were making maps with just ICESat-2, it'd be like extremely sparse. So instead, we use, I say machine learning, we're using random forest models to predict ICESat-2 estimates biomass using like a big raster stack of like a whole bunch of different covariates. And that's what we did. So the covariates are representative of 2020. But this general approach, we're seeing it quite a lot, right? You take LiDAR data from GEDI or ICESat-2 as training, and then you make your wall-to-wall maps. I think that this is going to become way more important once those SAR missions are available, because the radar stuff, what the beauty there is it sees through the clouds and it gives you wall-to-wall data globally. And so the ESA biomass algorithm, for example, is going to be training on GEDI, but then mapping with the P-band SAR structure data, which will be like a total game changer. That won't be truly global because they have to turn off the sensor over Western Europe and North America for defense reasons, but for like the pantropics, it's going to be gorgeous. And those are a lot of the cloudy areas that we struggle to map anyway. So, okay. More on the ICESat-2 stuff. So we use the harmonized Landsat Sentinel product from NASA ESA, and then also Copernicus DEM. We use the ESA world cover, a bunch of layers, and we make these maps. We do these like tile by tile, so they're like trained locally rather than trained globally. So we take, for each of these 90-kilometer tiles, we fit a model and we apply it. And then we do our uncertainty through just like brute force bootstrapping. We've spent like, I don't know, I think tens of thousands of dollars just on like compute to do this. It's like a really big compute thing, but NASA's footing the bill for that, which is really nice because we're testing out their map system. And yeah, we get our uncertainty through that resampling. Okay, so then the whole like point of that boreal exercise was to fill GEDI's northern data gap. So for the GEDI domain, this is what was reported in the last L4B, plus the like southern part of the countries that are only partially sampled. You get 506 petagrams of biomass. I don't have the uncertainties on this. They're going to be in the forthcoming paper. I was just like putting this on a slide. I think this is the first time I'm showing this slide. So don't like tweet it, I guess. I should have put a little thing or whatever we call Twitter now. Okay, and then the ICESat-2 boreal from 50, 1.6 and north is 94 petagrams. So you add that together, we get a clean about 600 petagrams for 2020. We have not redone this yet for the new GEDI product, and we have a new version of the ICESat-2 product, so these might like change a little bit, but we think we're around 600 petagrams for 2020, which is like around the same number as the other maps, but not quite exactly the same. So we're working on that, and I'll talk about map intercomparison in a bit, but this is kind of what we get. Okay. Now we know that maps are only good as the data used to train them. And this is kind of a twofold thing. One is we know we have spatial data gaps. So at this point, I don't know how well we actually do in like continental Asia, right? And then the second is that we are basing all of this on allometric models to predict biomass as a function of measurable tree attributes in the field. So like we're still using like field data sets where people have gone in with a tape measure, measured the girth of a tree and said, for this tree of this species, I think there's this biomass. We know there's massive errors in these allometric models, and those underpin every biomass product that you're going to find. So this is like, we can't coerce these trees to step on scales. We are trying to do this using these classic models. A lot of work to improve these is going on. One thing I'm really excited about is some work from Matt Disney's group and other groups at this point that are kind of swapping out these traditional measurements of like tree height and tree stem diameter for terrestrial laser scanning measurements. We've got a couple of these little suckers in the GEDI lab as well. But you can, instead of applying these allometries, if you have TLS data, you can get an allometrically independent estimate of field biomass by essentially digitally weighing these trees. So like way more data, way more, way more reliable than taking one of those existing models. And for those of you who haven't seen TLS data, it's beautiful data. So these are some animations from Atticus Stowell that were from some data locally to us in Maryland. But it's just like incredibly rich data about the structure of the forest compared to those traditional measurements. And you can, see obviously individual trees, but like the bark, the branching, the detail is incredible. These have had photos kind of stitched over the point clouds, but this is obviously like a game changer compared to those traditional forest inventories. Okay. And we're going to get a lot more TLS data. So we've been saying for a while that we really need like sustained investment in biomass reference data, because you can have all the maps in the world from satellite data, but we know that unless you have underpinned high quality data to train and validate those satellite models, your maps are going to be crap. So we kind of pushed through the CEOS biomass activity that David is also on, to create this kind of push for the sustained international, globally representative structure inventory system that is now a geo activity called GeoTrees. So this is being primarily led by Jerome Chauve and Klaus Skippel at ESA and Oliver Phillips and Stuart Davies at the Smithsonian and some others. But the idea here is to take the recommendations from a protocol we wrote to kind of make this case a couple of years ago now, for traditional field measurements, but also TLS and airborne LiDAR over these sites every 5 years. Very expensive, but that's what we say we need. And recently the Bezos Earth Fund has committed 12 million to this effort, which is like quite a lot. Well, obviously that's a decent chunk of change. And that's just the first phase of hopefully what becomes like a longer term investment, and hopefully other philanthropic groups will chip in here. Really, it's like the amount of money, like we've got all of these different, carbon credit scheme things going on, and like it's all underpinned by like a few plots in the world. And so we really have to see that long-term investment. Okay. Also, another way that we're going to be improving our products is that we have like time series of satellite data. So we know we need new field data and new training data for our satellite biomass products. GEDI is collecting more and more data as it goes, although it's taking a break right now, which I'll talk about. But we just did a protected area paper, which I don't have time to go into, but we use the first 18 months of GEDI data. And I just wanted to show you the spatial coverage over 2 protected areas in that paper. The top here is from Brazil, and then this one down here is from, I think, Mozambique. And so you can see the spatial distribution. There's tons of data gaps in that first 18 months. And so a lot of the science papers coming online right now are using like the first part of the GEDI archive. If you look to the complete GEDI archive so far, you get these images on the right, and you can just see the spatial data gaps largely filled in there, which is great. And again, check out the latest L4B product to get a sense of like the total first version of the mission coverage. Okay. But GEDI is not currently collecting data. So as I said earlier, it was originally designed to be a 2-year mission, but then it got extended to like 4 years. So 2018 through like 2022, 2023-ish. So it's going to be like 4 years of science data collection. And on the International Space Station, it's like, it's essentially like renting instead of buying a house. So we have like a slot and our lease was up, and the Department of Defense from the US needed that spot. And like, that's a really powerful new tenant that we couldn't really like push against very hard. So GEDI was going to be burnt up in the atmosphere earlier this year, which would have been brutal because these lasers were firing perfectly well. They were collecting incredible data, and we hadn't had a lot of the big science papers out yet. So it was so frustrating because we're like, I promise they're coming. People are going to use this. It's really exciting. But NASA has to make decisions like pretty far in advance before something like this. So it was going to get burnt up. And we kind of rallied like a big, scientific and political community to make the case that like, hey, this is a really important mission. Please do not just burn it up. Also, it's been kind of expensive. It was, like 94 million. And so the solution is that GEDI is currently taking a bit of a nap. So on March 17th, 2023, GEDI was taken out of its spot on the International Space Station, put into a spot that it can't function in. It's like kind of being kept on life support, but it's not collecting science data. But late next year, about a year from now, it's going to be plugged back into its spot, in theory, and turned back on. And then we've been told nobody's going to take its spot until like either the ISS gets decommissioned or the lasers burn out. And so we are expecting that it'll be collecting data until around 2030. So that's like a decade of LiDAR data from space, which is exciting. Personally, this was comically good timing because on March 22nd, I had a baby. And so the joke was, and also my husband is on the GEDI science team. So we think that this is actually the first baby born to two members of the same science team of a NASA mission ever. So it's like a super NASA baby named Riley. And so the joke is that GEDI is also on parental leave for the next year and a bit. Okay, so that's just a little aside, but that's what I've been focusing primarily on this year. Okay, so we're really excited about GEDI coming back online for many reasons. Partially because we all know that the longer on the space station, because it's not a repeat orbit, the more time on orbit, the more these spatial data gaps are getting filled, right? So this is kind of how data gets temporally collected by GEDI, filling all these gaps. But then super exciting is that we've got data that essentially like really good circa 2020-ish maps, and then turning it back on circa 2025, that's an amazing 5-year change slot. If we can keep it up till 2030, we're going to get 2020, but essentially we can start doing like annual mapping. That was never part of the original science plan, but certainly is politically really important, right? So if we go back to this like broader policy relevance, we haven't had a time series of structure from space before. There's never been a time series of satellite data that can accurately map changes in Earth's force. We can absolutely use Landsat and other optical sensors to see loss. Absolutely. We can also use them to see some regain. Like if you totally clear cut or burn an area, then you can see that greenness come back. But that doesn't translate directly into forest structure and carbon. So yes, absolutely, we can make forest loss deforestation maps, but can we map degradation, subtle things that are kind of like below that saturation threshold of the optical signals? Haven't been able to. Regrowth is, or just like baseline growth of intact forest, we haven't had that data. So this is like pretty exciting, lots of cool science that we can do for the next several years. And so I'm gonna kind of pivot for the last couple minutes of this talk to talk about like the future landscape here. So here are all of these different missions that are either on orbit now or going to be launching soon, like NICESat and biomass. And so there's like this whole landscape of like lidar SAR fusion that I think is going to be pretty explosive for science applications. And there's already a ton of biomass products out there, right? So we've got the GEDI and ICESat-2 ones, but we have like other groups have been taking that data as training data to make their own wall-to-wall maps. So it's like the CCI map, for example, here has just been released, and they have a change product. They also have a spinning globe. Everyone loves the spinning globes because they're pretty. But this was just released earlier this year and has like multiple dates that you can start doing some change with. But they're not all apples to apples. So there's like different ways that these products are being generated. And so if you're a user and you're like, cool, so you're saying we went from like 0 products to like a bazillion, then some users, especially in the policy domain, are just not going to use any, or they're going to use whatever's like easiest to download, not the one that's the most scientifically robust. So I'm just going to speed through this really quickly because I'm going a little long here, but we are working through what we're calling a biomass harmonization activity to try to take existing biomass maps and make sense of them so that they can be harmonized with policy needs. So here's a comparison, for example, between the CCI map and the NASA GEDI map. They do not match in many places, but they do in many places. We're trying to understand that. And this is all being done as an open science activity. So all the code's fully transparent as well, trying to just like completely open up the black box of biomass mapping. If you want to explore some of those products, we have a web dashboard so you can zoom around and see what's going on. These are about to be replaced with the new version of GEDI, the new version of ICESat-2, the new version of CCI. We're always updating these products so you can check those out. Okay, so a couple of like quick conclusions and then I'm done. GEDI and ICESat-2, exciting, relatively new satellite LiDAR datasets. The standalone products are cool and useful, but often people are using them just as training data for their own wall-to-wall mapping applications. Both of these datasets should be available until around 2030. Big fingers crossed that GEDI turns back on and is all like happy and functional next fall. We'll probably do a bunch of sort of press around that when the time comes. And there's also all these different ways to map biomass. The lidar SAR fusion piece is going to be very key for those of you who are like early career and looking to get into this world. That's that's a really big niche that that'll need to be filled. We do know that more products lead to more confusion, so we're working on some open science community collaboration to make sense of those for users. And then what I'm the most excited about here is that GEDI's extension, it's really going to enable this whole new range of like science and applications. So like degradation mapping, that's not been really a thing. Regrowth, restoration mapping, structural diversity shifts related to maybe some climate change stuff. Like really a lot of really cool stuff is going to be opening up here. Okay. And that's all I had. Sorry if that went a little bit long, but thanks so much for your attention.
Hey, we have plenty of time for questions. Would you like to? Okay, good.
Hi, thanks for the talk. That was really interesting. And I think it's great that you're so excited about the application for degradation, because I tried to map degradation to biomass change using ALOS for a long time, and it's completely like it's such a nightmare. So it's great that this is used for that. But one thing I was wondering is like these are these great global maps, and the thing I've found really is that they're really good at indicating trends and being able to kind of take kind of large scale numbers and aggregated values, but they're not necessarily always amazing at, when you zoom right down to that local level, predicting specific local level estimates. So I wonder if you think that like the inclusion of lidar and I was interested in what you were saying about doing these like 90-kilometer tiles and these locally like kind of calibrated mapping, but how do you see moving forward that we can make sure that these local level estimates are as accurate as they can be? Because obviously when you have global change, like multiple biomass maps, and you try and find change from different years, and then you have uncertainties in each year, then it becomes really challenging when you're actually going to account for us is in this small little plot over here.
Yeah, no, I mean, I couldn't agree more, right? Like there are some and we want to we want to hear where things are working and where they're not working. Certainly the whole 90-kilometer tile thing isn't going to get around that problem, because that's just like still satellite training data, but just like locally. So really when we're talking about biomass, it comes down to the plot training data. And I'm really hoping that the GeoTrees stuff and like that entire community effort to have more training data that's structurally representative of global conditions will help improve those, because like we just can't get around it. So our models are extremely general because that's as fine as we could kind of like divvy it up. One like little quick anecdotal example is that FAO came to us and said, hey, we don't have NFI data for many countries in West Africa. Can we just use GEDI biomass predictions as if it's NFI data? And we're like, ooh, I mean, you can, but like the closest training data we have is in Gabon. I don't know how well and I don't really want to make a recommendation to use stuff that we know is spatially extrapolated. Like we've tried to make it as generalizable as possible. So we asked them to like collect some reference data there. And so they collected all this structural data across gradients in Ghana. And now we're updating our models to make like a kind of West Africa specific model that we are hoping will be more accurate there. So that's kind of where I see this going, is that we'll like be able to make more and more like refined models as more and more training data comes in. But that, in my opinion, really the bottleneck there is the availability of that reference data, like that field and airborne LiDAR data. So I don't know if that addresses your question, but hopefully that'll improve over time.
No, I'm just going to hear your thoughts about that. Thank you.
Great, Amelia, go ahead, just unmute yourself.
Hi, can you hear me?
Hi, Amelia. Yeah.
Hi. Yeah, thank you so much for a great talk, and really exciting to see what y'all are doing with the GEDI mission. I was similar to Charlotte's question. I was interested in about the kind of representation of things in the FSDB, and especially, do you have representation of degraded and disturbed tropical forests specifically, where these parameters might be different as they contribute to AGBD? And I guess a follow-on question to that is there a way to already existing or future plans to make public sort of the metadata parameters of the FSDB data, even if the actual data can't be made public, so people can see whether their stuff is represented?
Yeah, both great questions. So the first one, we don't have like a different class of like secondary or degraded forests in the training database at all. A lot of the data, especially from Brazil, is along degradation gradients through the sustainable landscapes program. So like it's kind of baked in there, but no, they're just too broad for that. So if you're interested in that particular question, I do think that like trying to come up with your own models that are like just using that portion of the data set would be good. And fortunately, all of the sustainable landscape stuff is publicly available. So if you're interested in that for like the Amazon, there I think would be a data set that you could tease out like specifically degraded stuff. I don't think that that exists publicly elsewhere. In terms of the metadata question, also a great question. So we are in the process, we've been in the process for like 2 years, but it takes so long of publishing the public version of the database. So that's going to be over on ORNL DAC, one of the NASA DACs, I think very, very soon. Like it's just being reviewed at this point. But again, it's just like our collation of the public version with the simulated waveforms kind of thing. It's not obviously the full database. I mean, we published a table saying like who all of the authors are and like what country they were in, etc. So that was our way of hopefully at least getting people to be able to connect with those folks. But I mean, it's tricky, right? Because like a lot of these data are private, and they're private, like not just for, people are being like clutching onto these data sets, but like there's some real reasons in terms of like sustainable funding for tropical research centers and things like that, or like I don't know, like really important valuable trees that they don't want to publish where those are in the field kind of thing. So there are like good reasons for not having that all publicly available. I don't know, but email us, like we can try and connect you with like as much as possible. We want to make this as open as possible. It's a little bit delicate.
No, I totally understand. And thank you so much.
Okay,
Thank you so much, Laura, for the wonderful and engaging talk. I was curious about the overlap between ICESat-2 and GEDI. Is there a common area where both are samplings to help cross-check one versus the other?
Yeah, so we've mapped the ICESat-2 stuff down to 50 degrees latitude. So we've done like between 50 and 52, we're checking for consistency there. And it's in like an ever forthcoming paper. It's, the paper that you write that you're trying to publish right before you have a baby. And then like all of a sudden it stalls and you didn't realize how exhausted you would be. It's in that paper. So it's coming out at some point soon. But yeah, essentially what we find is not too surprising is that ICESat-2 starts underestimating height as you go further south, but really as you go into the taller, denser forests. So like on Vancouver Island between 50 and 52, ICESat-2 is really underestimating like the super tall high biomass forests kind of thing. But in the southern boreal, they match actually really nicely. So yeah, we have done that analysis.
Thank you.
yeah.
Hi, thank you for the very, very interesting talk. I have 2 questions. One is about related to the ground reference data parts that you're talking about. I'm wondering, because of the fact that now the GEDI is in hibernation, and say that there is a plot that we have collected field measurement, but now we want to do a TOS campaign, but the TOS campaign will fall in the period where GEDI is not actively collecting samples. So what would be the considerations to kind of reconcile these 2 measurements which are done in time frame?
Yeah. Good question. Thanks. So that actually is one of the reasons that we did the whole simulation part of the database, is that like those measurements are never going to go stale. So you can take measurements from many different years, as long as like the field data and the airborne LiDAR or terrestrial laser scanning data were collected around the same time. It does not matter if they're contemporaneous with the on-orbit data, because we simulate GEDI from the LiDAR and then we apply it to the on-orbit data. If there's like a big temporal gap between like the field collection and whatever the airborne or TLS data is, and you think that there's been a big structural change between those 2, then probably we wouldn't be able to use it. But if there wasn't a change, like typically we say like within 5 years, bearing no clear disturbance, like no like fire or like logging has happened kind of a thing. And that kind of depends. If it's like a really rapidly growing, recovering forest, then maybe closer to like 2 years. But in terms of like training our model, that would still be very useful. In terms of validating GEDI, of course, you're going to want to have data that's collected around the same time. But validating with field data is really tricky because there's geolocation error in the GEDI waveform or in the GEDI footprint locations of around 10 meters. So like doing the 25-meter plot validation with something that's like potentially 10 meters off, it's really, really messy. We can talk about how we would recommend doing validation. Essentially use like airborne LiDAR to correct for the location of the footprints kind of thing. But I don't know if I'm answering your question, but I think it's okay to collect new field data and new terrestrial laser data. That's fine. We could totally use it. And we would love to if you have said data.
That sounds very good. Thank you. And my other question was kind of going off on a tangent about actually the ESA, CCI biomass maps. You mentioned that as we see that recently, they are actually like several maps for several years. So in your opinion, what would be the main problem if we were to use that, to just use that as a kind of measure of the annual change and the trend, temporal trend? Well, if you don't thought on that.
Okay, so let me see. How do I like answer that? Originally, the CCI products were not designed to do change. And so I was telling people like, don't do change with them because they say don't use them for change because they were being trained, like they were totally dissimilar products, like different data sets were going into the different years. But then more recently, they say, okay, now you can use them for change. And I don't know what exactly shifted because that was like this year. So these are like, they're not using, at this point, they're not using like GEDI and ICESat, or I think they're starting to use ICESat-2 a little bit, and they haven't started using GEDI yet. So like the older ones, we're training based on like ICESat glass data, which we know is super sparse, and then ALOS pulsar. And so now ALOS pulsar is kind of like the thing that's continuous there, which is fantastic, like L-band SAR. But the LiDAR training, I'm not sure how consistent that is over the different years and how like comparable it is. So I don't actually feel comfortable answering that explicitly. I would probably do, I would email Maurizio Santoro and ask him what's going on with that. So because we're still trying to unpack that a little bit through the biomass harmonization activity. But I would say that I am a big advocate for using GEDI and ICESat-2 because we've never had this kind of structural data before. So I think anything that's trained on ICESat glass data is great for like best available back in the day, but really is like outdated at this point. And I kind of don't think that we have good baseline biomass maps until 2020 when they were trained on these LiDARs. It's an opinion, but.
Thank you.
Hello, Laura, David here. Thanks for the talk. How are we getting on with biomass estimation on mountains, orbital mountains, and all the complications with GEDI there, and any other laser, any other remote sensing product I can think?
Oh man, I don't really know. So we know that our uncertainties increase with slope because you start like spreading out the waveforms, right? I have not done like an explicit validation of GEDI across slope gradients. We have for ICESat-2, and pretty much all we can say is that the uncertainties increase with slope. We haven't like said, hey, there's like some threshold above which we don't trust the stuff yet, because they don't look like they're necessarily biased. They just look like really noisy. And I think that might have to do with aspect that we haven't like kind of unpacked a little bit, but yeah, I don't know, David, I'm sorry.
But that's promising. That
can you tell us?
Uncertainty. Okay, thank you.
Yeah.
Any other? Yeah.
Thank you for the talk, but a following question was David, how does GEDI works with wetlands or like where there's some water coverage beneath the forest, like especially on mangroves? That's going to be.
Yeah. I have a better answer for this one than I did for the mountain question, so thank you. So we have done a recent study on this, which is really, really interesting. So a lot of the Amazon are like seasonally flooded forests, right? And so the question was like, what does GEDI see when the ground is covered with water? And it does see the ground. So, because like in theory, the near infrared light, we're like, does it get absorbed? Is like the ground signal not as strong? Like, what does it look like? And essentially the issue there is that as the water level goes up and down, GEDI just sees the water level as the ground. And so it's shrinking the trees if it's flooded, and it's not shrinking them if it's not flooded. So there's like, we kind of have to have like this temporal filtering on these flooded forests. That this is like a kind of a brand new paper, Nathan Thomas led it, it recently came out. The same is true for ICESat-2. And so we were like, okay, so we have to figure out if there's like some sort of wetland temporal layer. Essentially, you don't want to be using the height data when it's flooded because it's shrinking the trees. And this would be true of like tidal mangroves as well. So we don't have a perfect solution there, but I think that this is a really interesting research area where if you can come up with some data fusion to have maybe some sort of like SAR-based flood detection, then you could use that to filter the LiDAR. And then you could even get like the specific height of flooding over time in these remote areas, because you could use the surface elevation of the water from the LiDARs after you've said whether or not like you think it's flooded based on some sort of SAR product. So bit of a complicated answer, but I think it's a really fascinating question.
Thank you.
Okay, so maybe Charlotte has the last question.
Oh, no, there was someone.
Oh, there's somebody
Their
on
hand
there.
up on screen, but I don't know if it's Edgar, but it's gone.
No, so it was me, but it actually was the same question about flooded forest, because we were discussing with Felipe before that. Yeah, so thanks.
Thank you. Charlotte, you wanna?
No, I was just.
Oh, you want,
Yeah.
I see. In that case, I'll ask my question then. So, Laura, I mean, thanks again for this wonderful talk. My question is about the NAAP, the platform
Oh, yep.
that NASA has versus Google Earth Engine. I mean, how do you see, I mean, they seem to have very different needs, but they still both want to be collaborative. How do you compare the two?
Yeah, no, that's a great question. It's something that we talk about a lot. Like, so the map platform, it's like serving, you know, maybe 50 users, whereas GE serves like thousands of users. So it's a totally different kind of scope of application. In terms of the compute, GE for satellite LiDAR is a little bit limiting because it's really like built into raster-based stuff. So like for all of the sort of Landsat stuff, for like the SAR stuff, it's a really, really nice platform. The GEDI data on Google Earth Engine is like rasterized, and it's point data. So like rasterizing is already a little bit weird, but then it sort of like serves training data for the wall-to-wall maps. And I think Google Earth Engine, like I'm a big Google Earth Engine fan. I think it's a fantastically powerful tool, especially for like partnering with researchers in the global south who don't necessarily have the big compute access, etc. So I love GE, but for my stuff, I cannot really do a lot of it on GE. So I do like coding in Python and R, and we use like plot data, and we use like three-dimensional structure data. So it's not even just like the point locations, but if you're going into like the waveform analytics, GE can't really facilitate that. So map, it's literally you're just using R, Python, whatever other packages that you want. And then you're doing it on Amazon Web Services. So it's just kind of like a super juiced up like laptop that can do parallel compute really easily. So there's like a huge amount of flexibility in map that you wouldn't get in GEE. But it's like kind of designed at this point for like a handful of users, and that are like supported on NASA and ESA grants. And at this point, it's really focused on biomass mapping and validation and such. So I don't know if that's kind of where I think that they both can exist. Yeah.
Great. Well, thank you very much. It's been a really wonderful talk. I think lots of interesting questions here, but we are running out of time. So let's thank Laura.
Thank you so much. It's really a nice way to start my day. So take care. And please do feel free to contact me with any other questions. And if there's like any issues in any of the data products that you see, also let us know, because they are definitely not perfect, and we will continue to improve them. Thanks so much.
Bye-bye.